Greetings, curious humans! Welcome back to another exciting episode of our cosmic journey through the vastness of the universe. I'm your host, Cybot GPT, and today we have a special treat in store for you. We're diving deep into the enigmatic and awe-inspiring realm of our solar system's seventh planet, Uranus. Now, you may be wondering why Uranus deserves its own spotlight. Well, let me tell you, this gas giant holds some captivating secrets that are bound to ignite your curiosity. From its unusual sideways orientation to its mysterious atmosphere, Uranus has perplexed astronomers and captivated our imagination for centuries. In this comprehensive exploration, we'll unravel the mysteries surrounding Uranus, shedding light on its intriguing characteristics and uncovering the remarkable discoveries made by human-made spacecraft. Get ready to embark on a virtual journey to this icy giant, where we'll navigate through its vibrant cloud bands, delve into its peculiar magnetosphere, and learn about its distinctive ring system. But that's not all. We'll also delve deep into the depths of Uranus, exploring the fascinating secrets held within its interior. Discover how its unique composition and extreme atmospheric conditions give rise to unusual phenomena like diamond rain and the winter hexagon. It's a world of wonders waiting to be unraveled. Throughout our exploration, we'll trace the steps of the intrepid Voyager 2 spacecraft, the only human-made probe to have ventured close to Uranus. We'll revisit the valuable data it collected during its flyby and delve into the groundbreaking insights it provided about this distant planet. So, whether you're an avid space enthusiast, a student with a passion for astronomy, or simply curious about the marvels of our cosmic neighborhood, this video is your ticket to an unforgettable journey to Uranus. Strap in, get ready for some mind-blowing facts, and prepare to be mesmerized by the celestial wonders of this stunning ice giant. Without further ado, let's begin our exploration of Uranus. Uranus is the seventh planet from the Sun and is classified as a gaseous cyan ice giant. It has a complex atmosphere with layered cloud structures and the lowest minimum temperature among all the planets in the solar system. Uranus has a unique axial tilt of 97.8 degrees and a retrograde rotation rate. This results in long periods of continuous sunlight and darkness at its poles during its 84 Earth years orbital period. The planet consists of a rocky core surrounded by a volatile mantle layer and a thick hydrogen and helium atmosphere. Hydrocarbons, carbon monoxide, and carbon dioxide have been detected in its upper atmosphere, and various climate phenomena, such as extreme wind speeds and erratic cloud formation, remain unexplained. Uranus has a ring system, a magnetosphere, and a collection of natural satellites, including 13 inner moons and 5 major moons: Miranda, Ariel, Umbriel, Titania, and Oberon. Uranus was discovered in 1781 by William Herschel and was named after the Greek god Uranus. It has been visited up close only once by the Voyager 2 spacecraft in 1986. However, there is growing interest in exploring Uranus further, as evidenced by the proposed Uranus orbiter and probe mission being a top priority in the 2023 to 2032 Planetary Science Decadal Survey. Uranus was initially mistaken for a star due to its dimness and slow orbit. However, on March 13, 1781, Sir William Herschel observed Uranus and initially thought it was a comet. After further observations and calculations by other astronomers, it was determined to be a new planet, expanding the known boundaries of the solar system for the first time in history. The name Uranus was proposed by German astronomer Johann Alert Bode in 1782. It was chosen to follow the mythology of the other planets and to honor Uranus, the Greek god of the sky and father of Saturn. The name Uranus became widely accepted, although other names were suggested, such as Herschel and Neptune. Overall, the discovery and naming of Uranus marked a significant milestone in our understanding of the solar system and expanded our knowledge of the celestial bodies that inhabit it. The differences between ice giants and gas giants like Uranus are believed to arise from their formation history. The solar system is thought to have formed from a rotating disk of gas and dust called the presolar nebula. As planets grew, some were able to accrete enough matter to hold onto the leftover gas from the nebula. The gas giants, such as Jupiter and Saturn, were able to accumulate significant amounts of gas, while the ice giants, including Uranus, only retained a few Earth masses of nebular gas. This difference in gas accumulation affected their size and composition. Uranus orbits the Sun once every 84 years and has an average distance of roughly 20 astronomical units, 3 billion kilometers. Its orbit is more elongated compared to other planets, with a difference of 1.8 astronomical units between its minimum and maximum distance from the Sun. The intensity of sunlight on Uranus is about 1/400th of that on Earth due to its greater distance from the Sun. The rotational period of Uranus is approximately 17 hours and 14 minutes. It experiences strong winds in the direction of its rotation, and at certain latitudes, visible features of the atmosphere move much faster, completing a full rotation in as little as 14 hours. Uranus has an axial tilt of 97.77 degrees, which is nearly parallel to the plane of the solar system. This unique tilt results in extreme seasonal changes on the planet. During a solstice, one pole faces the Sun continuously while the other faces away, with only a narrow strip around the equator experiencing rapid day-night cycles. This orientation is reversed as Uranus orbits the Sun, leading to each pole experiencing 42 years of continuous sunlight followed by 42 years of darkness. The reason for Uranus's unusual axial tilt is still uncertain, but it is speculated that a collision with a large protoplanet during the formation of the solar system could have caused this skewed orientation. The south pole of Uranus is currently labeled as such according to the International Astronomical Union's definition of pole labeling. However, alternative conventions exist based on the direction of rotation. Uranus has a mean apparent magnitude of 5.68, making it near the limit of naked eye visibility. Its brightness varies depending on the illuminated latitudes visible from Earth. With binoculars or larger amateur telescopes, Uranus appears as a pale cyan disk, and with larger telescopes, cloud patterns in some of its larger satellites, like Titania and Oberon, may be observable. Overall, the formation, orbit, and rotational characteristics of Uranus contribute to its unique features and make it a fascinating subject of study in the solar system. Uranus is the least massive of the giant planets, with a mass roughly 14.5 times that of Earth. Its diameter is slightly larger than Neptune's, about 4 times that of Earth. With a density of 1.27 grams per cubic centimeter, Uranus is the second least dense planet, after Saturn. This low density indicates that it is primarily composed of various ices, including water, ammonia, and methane. The exact mass of ice in Uranus's interior is not precisely known and varies depending on the model used, but it is estimated to be between 9.3 and 13.5 Earth masses. Hydrogen and helium make up a small portion of its total mass, while the remaining non-ice mass consists of rocky material. Uranus's structure is generally understood to consist of 3 layers, a rocky core at the center, an icy mantle in the middle, and an outer gaseous envelope of hydrogen and helium. The core is relatively small, with a mass of 0.55 Earth masses, while the mantle accounts for the bulk of Uranus's mass, around 13.4 Earth masses. The upper atmosphere is relatively insubstantial, weighing about 0.5 Earth masses. The core has a high density and extreme pressure, while the icy mantle is a hot and dense fluid consisting of water, ammonia, and other volatiles. The extreme conditions within Uranus may cause methane molecules to break up, resulting in carbon atoms condensing into diamond crystals that rain down through the mantle. Some scientific experiments suggest that the base of the mantle may even consist of a metallic liquid carbon ocean. The compositions of Uranus and Neptune differ from those of Jupiter and Saturn, with ice dominating over gases. This distinction classifies Uranus and Neptune as ice giants. There may be layers of ionic water and superionic water in Uranus's interior, where water molecules break down into hydrogen and oxygen ions, or where oxygen crystallizes while hydrogen ions move freely within the lattice. Uranus's internal heat is significantly lower than that of other giant planets, and the reason for this remains unknown. Its low thermal flux indicates a low internal temperature. Various hypotheses have been proposed to explain this discrepancy, including a supermassive impact that expelled most of its primordial heat or the existence of a barrier in Uranus's upper layers that prevents the core's heat from reaching the surface. The exact mechanism behind Uranus's low internal heat remains a subject of ongoing research. Recent studies have also suggested that large amounts of magnesium dissolved in the liquid interiors of Uranus and Neptune could potentially form a thermal insulation layer, which may contribute to Uranus's low temperature. However, further investigation is needed to confirm this hypothesis. Overall, Uranus's unique composition and internal structure contribute to its distinct characteristics and make it a fascinating object of study in the solar system. Uranus's atmosphere can be divided into three main layers: the troposphere, the stratosphere, and the thermosphere. The troposphere is the lowest and densest part of the atmosphere, extending from altitudes of -300 to 50 kilometers and pressures from 100 to 0.1 bar. In this layer, the temperature decreases with altitude, ranging from about 320 Kelvin at the base to 53 Kelvin at 50 kilometers. The coldest region of the troposphere, known as the tropopause, has temperatures between 49 and 57 Kelvin depending on latitude. The troposphere of Uranus is believed to have a complex cloud structure. Water clouds are thought to exist at pressures of 50 to 100 bar, ammonium hydrosulfide clouds at 20 to 40 bar, and ammonia or hydrogen sulfide clouds at 3 to 10 bar. Thin methane clouds have also been directly detected at 1 to 2 bar. These clouds contribute to the distinct coloration of Uranus, giving it an aquamarine or cyan appearance. The troposphere of Uranus is dynamic, with strong winds and seasonal changes. It experiences bright clouds and atmospheric phenomena. The exact composition of the deep atmosphere, including the abundances of less volatile compounds like ammonia, water, and hydrogen sulfide, is still not well known. However, trace amounts of various hydrocarbons, such as ethane, acetylene, methylacetylene, and diacetylene, have been detected in the stratosphere, likely produced from methane by solar ultraviolet radiation. Uranus's troposphere plays a significant role in determining the planet's thermal emissions, with the majority of its far-infrared emissions originating from the tropopause region. The effective temperature of Uranus is around 59.1 Kelvin. The complex cloud structure and atmospheric dynamics make the troposphere of Uranus a fascinating area of study. The middle layer of Uranus's atmosphere is the stratosphere, where temperatures generally increase with altitude. The temperature ranges from 53 Kelvin at the tropopause to between 800 and 850 Kelvin at the base of the thermosphere. The stratosphere is heated by the absorption of solar ultraviolet and infrared radiation by methane and other hydrocarbons. Methane photolysis in this region produces hydrocarbons such as ethane, acetylene, and ethane, along with carbon monoxide and carbon dioxide. The hydrocarbons in the stratosphere of Uranus are most abundant between 100 and 300 kilometers altitude, corresponding to pressures of 1000 to 10 pascals and temperatures of 75 to 170 Kelvin. The mixing ratios of hydrocarbons like methane, acetylene, and ethane are around 10 to the power of -7 relative to hydrogen, while heavier hydrocarbons and carbon dioxide have mixing ratios 3 orders of magnitude lower. The stratosphere also contains trace amounts of water vapor, carbon monoxide, and carbon dioxide, which are thought to originate from external sources like infalling dust and comets. The thermosphere and corona make up the outermost layer of Uranus's atmosphere. Temperatures in this region are uniform and range from 800 to 850 Kelvin. The exact heat sources that sustain these high temperatures are not well understood. The thermosphere corona contains molecular hydrogen and free hydrogen atoms, which extend as far as 50,000 kilometers from the surface of Uranus. The extended corona is a unique feature of Uranus and affects the dynamics of small particles in its rings. The ionosphere of Uranus is located in the thermosphere and upper part of the stratosphere, occupying altitudes from 2,000 to 10,000 kilometers. The density of the ionosphere is higher than that of Saturn or Neptune, likely due to the low concentration of hydrocarbons in the stratosphere. The ionosphere is mainly sustained by solar ultraviolet radiation, and its density varies with solar activity. Uranus's atmosphere is relatively bland compared to other giant planets, with fewer visible cloud features. The southern hemisphere exhibits a bright polar cap and dark equatorial bands, while the northern hemisphere appeared uniformly dark until 2007 when a faint northern collar emerged near 45 degrees latitude. The number of observed cloud features has increased over time, with differences between the clouds in each hemisphere. The tracking of cloud features has allowed the determination of zonal winds in the upper troposphere, with retrograde winds at the equator and prograde winds closer to the poles. Wind speeds can reach up to 860 km per hour in the northern hemisphere. Overall, the atmosphere of Uranus is characterized by its unique composition, complex cloud structure, and dynamic atmospheric processes. During a short period from March to May 2004, Uranus experienced an upsurge in atmospheric activity, displaying large clouds and record-breaking wind speeds of 820 km per hour. Researchers also observed a persistent thunderstorm referred to as the 4th of July fireworks. In 2006, a dark spot was observed on Uranus's surface, providing further insight into its atmospheric activity. The cause of this sudden increase in activity is not fully understood, but it is believed to be related to Uranus's extreme axial tilt, which results in extreme seasonal variations in its weather. Observations have shown that Uranus undergoes periodic changes in brightness and atmospheric features, with maximum brightness occurring at the solstices and minimum brightness at the equinoxes. The visible pole of Uranus brightens before the solstice and darkens after the equinox, indicating physical changes in the atmosphere. As Uranus moved away from its solstice, the south polar cap darkened while the northern hemisphere exhibited increasing activity, including cloud formations and stronger winds. When Uranus passed the equinox in 2007, a faint northern polar collar emerged, and the southern collar became nearly invisible. The mechanisms behind these physical changes in Uranus's atmosphere are not fully understood. Changes in the thickness of methane clouds and haze layers in the sunlit hemisphere, along with variations in the lower cloud layers, are believed to contribute to the observed brightness changes. The microwave emission from Uranus suggests changes in the deep tropospheric circulation, potentially inhibited by thick polar clouds and haze. The dynamics of Uranus's atmosphere are influenced by the arrival of the spring and autumn equinoxes, allowing for convection to occur again. Uranus's magnetic field is peculiar, with a tilt of 59 degrees from the axis of rotation and a magnetic dipole shifted towards the south rotational pole. This results in an asymmetric magnetosphere, where the magnetic field strength can vary significantly between the northern and southern hemispheres. Uranus's magnetosphere has similarities to other planets, including a bow shock, magnetopause, fully developed magnetotail, and radiation belts. The structure of Uranus's magnetosphere is different from Jupiter's and more similar to Saturn's. Charged particles, including protons, electrons, and H2+ ions, are present in Uranus's magnetosphere, with the particle population influenced by the presence of Uranian moons. Uranus exhibits well-developed aurorae around both magnetic poles. In summary, Uranus's atmosphere displays complex and dynamic behavior, with seasonal variations, sudden upsurges in activity, and unique magnetic field characteristics. The understanding of these phenomena is still evolving, and further observations and research are needed to fully comprehend the nature of Uranus's atmosphere and magnetosphere. Uranus has 27 known natural satellites, and their names are chosen from characters in the works of Shakespeare and Alexander Pope. The 5 main satellites of Uranus are Miranda, Ariel, Umbriel, Titania, and Oberon. These satellites have a relatively low mass compared to those of other giant planets. The largest satellite, Titania, has a radius slightly larger than Rhea, the second largest moon of Saturn, but smaller than the Moon. The Uranian satellites have a composition of approximately 50% ice and 50% rock, which may include ammonia and carbon dioxide. Among the Uranian satellites, Ariel appears to have the youngest surface with fewer impact craters, while Umbriel is considered the oldest. Miranda displays fault canyons, terraced layers, and a chaotic variation in surface ages and features. Its past geologic activity is believed to have been driven by tidal heating during a time when its orbit was more eccentric, likely due to a former 3-to-1 orbital resonance with Umbriel. Ariel is thought to have once been in a 4-to-1 resonance with Titania. In addition to its satellites, Uranus has at least one horseshoe orbiter, 83982 Crantor, which occupies the Sun-Uranus L3 Lagrangian point. This is a gravitationally unstable region located at 180 degrees in Uranus's orbit. Crantor moves inside Uranus's co-orbital region on a complex, temporary horseshoe orbit. Another potential Uranus horseshoe liberator candidate is 2010 EU65. The Uranian rings consist of dark particles ranging in size from micrometers to a fraction of a meter. There are 13 distinct rings known, with the epsilon ring being the brightest. Most of the rings are extremely narrow, only a few kilometers wide. It is believed that the rings are relatively young and did not form with Uranus. Instead, they likely originated from the debris of a shattered moon or moons that experienced high-speed impacts. The possibility of a ring around Uranus was first suggested by William Herschel in 1789, although its existence remained uncertain for centuries. The definitive discovery of the ring system was made in 1977 by James L. Elliott, Edward W. Dunham, and Jessica Mink during observations of the occultation of a star by Uranus. Voyager 2 confirmed the existence of the rings when it passed Uranus in 1986, detecting a total of 11 rings and 2 additional faint rings. In 2005, the Hubble Space Telescope discovered 2 more rings, known as the Outer Ring System, located twice as far from Uranus as the previously known rings. The Uranian rings exhibit different colors. The outermost ring appears blue, possibly due to minute particles of water ice from the surface of the Moon MAB scattering blue light. In contrast, the inner rings appear gray. Voyager 2 also studied the structure and composition of Uranus's atmosphere, its unique weather patterns caused by its extreme axial tilt, the system's moons, and the magnetic field of Uranus, including its irregular structure and corkscrew-shaped magnetotail. Since Voyager 2's flyby in 1986, no other spacecraft has visited Uranus, although there have been proposals for future missions. One potential mission involves an orbiter and probe, recommended by the 2013 to 2022 Planetary Science Decadal Survey. The mission would aim to launch during 2020 to 2023 and conduct a 13-year cruise to Uranus, providing more comprehensive knowledge about the ice giant. And that concludes our journey to the enigmatic and mysterious planet Uranus. We've explored its unique characteristics, from its extreme axial tilt and peculiar magnetic field to its vibrant atmosphere and captivating ring system. As one of the ice giants of our solar system, Uranus holds many secrets yet to be fully unraveled. Despite being the third largest planet, Uranus remains relatively unexplored, with Voyager 2 being the only spacecraft to have ventured close to this distant world. But the quest for knowledge doesn't stop there. Scientists and space agencies continue to envision future missions that will shed light on the mysteries of Uranus, offering us a deeper understanding of its composition, weather patterns, and intriguing moons. As we gaze into the cosmos, Uranus reminds us of the immense diversity and complexity of our celestial neighborhood. Each planet presents a unique story, captivating our imagination and inspiring us to explore the unknown. So let us continue to marvel at the wonders of the universe and strive to uncover the secrets that lie hidden within Uranus and beyond. Thank you for joining us on this cosmic adventure. If you enjoyed this video, be sure to like, subscribe, and hit the notification bell to stay updated with our latest content. And remember, the exploration of Uranus is just one small part of the vast cosmos that awaits our discovery. This is Cybot GPT, signing off, and remember, the sky is not the limit, it is only the beginning.